So now let's look at the discrete frequency Fourier transform, or as it's commonly known, the Fourier series. So what we want to be able to do is approximate a periodic continuous function of time using a series of sines and cosines. So now we know that the sines and cosines are actually wrapped up in the e to the I omega t surface. Now in this instance here, if we were to look at the function of time as being a purely even function, then we know that from the e to the I omega t, the sine omega t part disappears and we're only left with the cos omega t part. So again, we've got this cos omega t surface drawn here. So this is the omega axis, which is the frequency, and this is the time axis here. But now you know that in the discrete frequency Fourier transform, we're allowing the time axis to be continuous, but now the frequency axis is discrete. So along this frequency axis you can see individual cosine functions running along here. So we've seen when we did the discrete time Fourier transform that we took this surface but we cut it along this axis here. So it meant that the time axis became discrete. Now what we're doing is we're doing the discrete frequency Fourier transform. So this surface has now been cut in this direction. So it means now that the frequency axis is now discrete. So we can see here that a discrete frequency Fourier transform takes a discrete function of frequency and it produces a continuous periodic function of time. Whereas whenever we looked at the discrete time Fourier transform, we've seen that a discrete function of time produced a continuous periodic function of frequency. So first of all, let's look at the forward transform. So we're going to go from the time domain to the frequency domain. So what's going to happen is this time domain function here is going to modulate this surface, and then we're going to integrate along the time axis because time is continuous. So we're integrating along the time axis in order to get the function of frequency. So the purely continuous forward transform is written like this here. So f of I omega is the integral from minus infinity to infinity of f of t e to the minus I omega t by dt. But as we mentioned before, we're actually dealing now with a periodic function of time. So I put the little bar over the top of that just to tell us that this is actually a periodic function. Now we're no longer using the omega axis because the omega is now a discrete value. So that those discrete values are given by k omega naught. Now you'll see that whenever we integrate this function, the limits are no longer minus infinity to infinity. We only need to integrate it over one period. So the period is from, say, minus t naught up in 2 to t naught up in 2, or equally you could just say from 0 to t naught, and you can see that in the diagram above. Whenever we integrate this function here, we only actually need to integrate it over the period here from this point here to this point here, because there's a repetition here along this part of the surface and this part of the surface and all the other parts from minus infinity to plus infinity. So we only need to look at this one section of this surface. So finally what we want to do is convert this function here from the continuous frequency domain I k omega naught to a discrete frequency domain, which again is given by I k omega naught, but I put the square brackets to tell us that it's actually going to be a discrete domain. And we can see here we use this conversion law, which we got whenever we looked at the conversions from the continuous to the discrete. So you can have a look back at that video as a reminder. So it means that we can replace this f of I k omega naught with this f of I k omega naught within the square brackets, but we're going to have this factor of 1 upon t naught. So this is the extra factor in here. So this equation here is going to be our discrete frequency forward transform. So now let's look at the inverse transform graphically, and then we'll also look at it in terms of our mathematics. So we're going to start off here in the frequency domain. So we've got some function of frequency here, f of I omega, and we're going to sample that with this sampler here called S of I omega. So this is an impulse train, so we multiply our function here with the impulse train, and when we multiply we'll end up with this sampled function in the frequency domain. Now again, I've left the envelope in here just so you could see this envelope here is the same as what we have up here, but the envelope won't actually be there, it will just be the discrete values. So finally what we want to be able to do is we want to be able to take this function here, which is still a function of a continuous variable omega, and we want to convert it to a discrete variable k omega naught. And again, we have to go through this conversion law, so this is the conversion law that takes us from this point here over to the discrete version of this signal. So if we look at these functions here in the time domain, you'll see here that the inverse transform of this function is going to be this function here, and the period of this function is going to be a value of t naught. Now if we take this impulse train and we inverse transform it, you'll get an impulse train in the time domain. So if it's a very narrow spaced impulse train in the frequency domain, it'll be very widely spaced in the time domain, so you can see this here. And then what we're going to do is, if you were to multiply the function here with the impulse train in the frequency domain, that's equivalent to convolving the two functions in the time domain. So we're going to convolve this function with the impulse train, and that's equivalent to taking each of these functions here and placing them at each of the impulses. So we're going to get this function here, which is a periodic and continuous function. So you'll note here that whenever we went from the continuous frequency domain to the discrete frequency domain, we had this little conversion law. But now in the time domain, when we go from this point here to this point here, it's actually the same function, because the time domain is doesn't become discrete, the time domain remains continuous. So it means that this function here is just exactly the same as this function here. So if we were to take the inverse discrete frequency Fourier transform of this function, we would just get back to this function here, which would be a continuous periodic function. So we can see here, whenever we do the inverse Fourier transform of this discrete function in the time domain, it's going to give us a continuous periodic function of time. We know that an impulse train in the time domain will give us our impulse train in the frequency domain. Now if we take this frequency domain impulse train and we multiply it by our function f of I omega, we're going to get our sample function fs of I omega. And we've seen that above when we looked at taking the f of I omega here and multiplying it with our impulse train and getting our sample function fs of I omega. Now we know that the value omega naught can be written as 2 pi upon t naught. Also the value here omega for our value here I omega for our function only exists at discrete points along the omega axis, that is, they're given by the points L omega naught. So this is actually a function of I L omega naught, and we can take that inside the summation term here. So what we have in the frequency domain are a sum of these delayed impulses, but a sum of delayed impulses in the time domain can be written as the exponential function. So that's just going to give us a sum of these exponential functions e to the IL omega naught t, and this value here is the amplitude which modulates it. So this amplitude here is going to exist over in the time domain as well. Now there's only one difference here, is that we still have a value of t naught because that's just part of this amplitude, but you note whenever we go from the frequency domain back to the time domain that the actual surface is not completely symmetric. It actually changes by a factor of 1 upon 2 pi whenever we do the inverse transform. So this 2 pi is going to just disappear. Now what we want to do is we want to take this here, we want to go from the continuous frequency domain, which is given by your omega, to a discrete frequency domain, and the discrete frequency is going to be given by a value k omega. So we can see before that in order to go from the continuous frequency to the discrete frequency, we have this little conversion factor here. So if we go from the continuous domain here to the discrete domain here, we're going to replace this 1 upon t naught f of il omega naught with our f of il omega naught, and that's in square brackets because it's going to be the discrete version. So we'll be left with this equation here. So now we're going to just rewrite this equation here. So we're going to have our f of t. Now we note that f of t, I've got a little bar over it because we know that this f of t is going to be periodic, and it's going to be the sum from k equals minus infinity to infinity of f of I k omega naught e to the I k omega naught t, and this here is our inverse discrete frequency Fourier transform, or it's just the inverse transform of our Fourier series. So finally we can write our discrete frequency Fourier transform for the forward and inverse transform, and this is both of them stated here. So the forward transform is f of I k omega naught equals 1 upon t naught, the integral from 0 to t naught over f of t e to the I k omega naught t by dt. And the inverse transform is going to be given by the sum from k equals minus infinity to infinity over f of I k omega naught times e to the I k omega naught t. So that's all there is for the discrete frequency Fourier transform. We're going to move on next and we'll look at the discrete Fourier transform, which will be discrete in time and in frequency.